In the final 3 videos, we will discuss strategies for integration. And the idea is to develop the mindset necessary to evaluate integrals. In the past, what we've seen with differentiation is that it's a very systematic procedure. You look at the function you're differentiating, and based upon its form, you immediately know what method of differentiation and which differentiation formulas you're going to apply. Integration is a very different procedure, and usually it requires a bit more ingenuity on your part. Now, the previous examples we've gone over, we've had a very nice luxury. We always knew what method of integration we were going to apply. That will no longer be the case. You can imagine that you might be given a list of integrals and asked to evaluate. So you're going to need to first determine the method to use, and once you've determined the method, then you will evaluate. So going back to our original video in this section, here's the table of common antiderivatives at a minimum that we should all have committed to memory in the sense that we can easily recall and use them as necessary. If you look at an integral and you immediately know how to evaluate it, then you do so. If not, these steps are going to give us a few mental processes to go through to determine the method of integration. So the first thing we want to ask, is it one of these standard integrals? Is it something that we can, through a little bit of algebraic manipulation, get back to our common antiderivatives? If not, can we algebraically simplify the integrand to maybe do a substitution or compare to the table? And here's kind of a common example. When you first look at it, it may not immediately be clear what we can do, but note e to the 2x is really e to the x times e to the x. So with this in mind, we can now do a substitution. And for the substitution, there are a couple choices, but I think a particularly nice choice is to choose u to be maybe the largest possible inside function. So we let u be 1 plus e to the x, so that du is e to the x dx. And looking over at our integral, 1 plus e to the x is u, e to the x dx is du, and then that leaves us remaining e to the x. But if we look at our substitution, that gives us a relationship between e to the x and u. E to the x is going to be u minus 1. So very quickly this integral becomes u minus 1 over u. And that is a much more reasonable integral for us to evaluate because it simplifies algebraically into just 1 minus 1 over u. The antiderivative, u minus ln, absolute value u plus c, and then we resubstitute in 1 plus e to the x minus the natural log of 1 plus e to the x plus c. So the observation is, starting with our integral, can we compare it immediately to our table? If not, algebraically simplify. Are there any simplifications possible? Things to be aware of are dealing with exponential properties. E to the 2x is e to the x times e to the x. And now to continue on our strategies. So is it a standard integral? That is, does it compare to the table of common antiderivatives? Okay, if not immediately, try algebraic simplification. Look for obvious substitutions. If you find no obvious substitutions, continue on. Based upon the form of the integrand, we should have a possible method of integration. If it's a trigonometric function, does it compare to our common trigonometric integrals? If it's a rational function, we could try to do a partial fraction decomposition. For functions of the form polynomial times cosine or sine, polynomial times an exponential, and so on, apply integration by parts. If it contains one of the desired expressions for a trig substitution, apply the trig substitution. Then afterwards, we go into maybe some more subtle things. So if there's not an obvious substitution, is there something more subtle, like a rationalizing substitution? Is there any possible way you can try integration by parts? And are there more advanced ways to manipulate the integrand? So let's go through a few more examples and kind of see if we can develop this mental mindset, at least give you an idea of what I'm thinking as I approach these integrals. So given the definite integral, 1 over 1 minus t squared. It does not immediately compare to one of my integrals. If it happened to be a plus instead of a minus, it certainly would. There's no obvious simplification or substitution, but this does fit one of our standard forms. It's a rational function, and to integrate rational functions, we can use a partial fraction decomposition. So we do our algebra to the side here. 1 over 1 minus t squared is 1 over, it's a difference of squares, 1 minus t times 1 plus t. So the partial fraction decomposition contains two terms. A over 1 plus minus t plus b over 1 plus t. Take this denominator on the left, multiply each term by it, and we will have 1 is equal to a times 1 plus t plus b times 1 minus t. And because we only have distinct linear terms, we can simply plug in intelligent choices to solve for the constants. For example, if we plug in t equals 1, the b term vanishes, and 1 is equal to 2a, so that a is equal to 1/2. If we plug in t equals minus 1, the a term will vanish, and what we are left with is 1 is equal to minus 2b, so that b is equal to minus 1/2. So in this case, the partial fraction decomposition is very quick, very efficient. So now we go ahead and apply that. Our integrand, so we're still integrating from 0 to 1/2, but the integrand can be written as a over 1 minus t, so 1/2 over 1 minus t, plus b, so that'd be minus another 1/2 over 1 plus t. Now we integrate each of these terms individually. So for the first one, we're going to have 1/2 and then 1 over 1 minus t. Its antiderivative is going to be the natural log of 1 minus t. And because of the minus sign that we have in front of the t, we need a minus sign out front. And in order to see where that minus sign comes from, you could do a u substitution, u equals 1 minus t, or you could double check this in terms of a derivative with the chain rule. Then for the second piece, we have minus 1/2 natural log absolute value 1 plus t, and we evaluate from 0 to 1/2. So we have a minus 1/2 that pulls out front, and then we plug in a 1/2, so that would be natural log of 1/2, plus, because we've pulled out a minus 1/2, natural log of 3/2, and then we subtract away what we get when we plug in 0. Natural log 1 plus natural log 1. Since the natural log 1 is 0, what we are left with is simply the minus 1/2 natural log of 1/2 plus the natural log of 3/2. You could simplify the natural logs a bit here, but I think that this form of the solution is certainly fine.